All right, let's get started. Hello, everyone. Welcome to Penn State CTISI's BERD seminar series. My name is Lan Kong. I'm professor of biostatistics in the Department of Public Health Sciences. I'm going to co-host on this seminar series with my colleague, Professor Terry Murphy. If you have any questions regarding BERD seminar, please feel free to reach out to us using this email address. So for this fall semester, we are happy to announce 7 excellent presentations. They are all scheduled on Mondays from 1 to 2 p.m. Through Zoom webinars. You can register for any of these seminars using this link to the Penn State News website or through this QR code for convenience. So for those of you who joined the BERD seminars for the first time, I would like to go over some Zoom webinar logistics. So first of all, you're probably aware this seminar is automatically recorded. Please mute your microphone during the presentation. You can ask questions using the chat feature during the lecture, or save your questions to the end of the seminar where we have a Q&A session. You will receive the presentation slides, recording link, and a short survey asking your feedback about seminar after the seminar. So now it's my great pleasure to introduce our speaker today, Dr. Ajit Vamuri. He is a computer scientist in the Department of Neurology and Public Health Sciences. He received his PhD degree in computer science from the University of Delaware in 2024. His primary interest of research is in the area of developing and applying wearable technology for real-time detection of behavior patterns and the delivery of interventions to enhance physical activity. He also has expertise in analyzing multimodal data sets, including electronic health records data based on machine learning techniques to predict clinical events such as stroke recurrence and hemorrhagic transformation. So today, he will share his research and work on designing adaptive interventions through wearables to improve physical activity. So welcome, Dr. Vamuri. Please take it away. You can share on screen your slides.
Yeah, thank you so much, Lan. I would really like to thank you and Terry to give me this opportunity to present at this seminar. I'm going to start sharing my screen. Please let me know if you see the slides. Do you see the full screen?
Yes.
Okay. Thank you everyone for attending this talk. As Lan mentioned, the title of the talk is Designing Adaptive Interventions Through Wearables to Improve Physical Activity. So the outline of this talk is as following. So I'm going to introduce you to 3 different ideas. So in 3 different kind of studies that we kind of did. So this is not an overview of developing wearable interventions, but this is more like an overview of what I have done recently. And as the wearable space, especially the just-in-time adaptive intervention space, is really new. So majority of the results that I show you are mostly pilot studies and then some of the algorithms that we have built to deploy into some of the studies that we are planning in future. So let's And then there is one last thing that I want to talk about is that most of the slides here are going to give you a computational view of how to design these interventions rather than a methodological or a behavioral science point of view. So here is a good picture to represent what are the factors influencing physical activity. So there are multiple determinants of physical activity. So in the bottommost layer, so it is mostly based on your motivation skills. So how is your self-efficacy? How interested are you to change behavior? How good are you to how resilient are you to what do you call when you fail? So all of those come under the individual or the psychological determinants that affect physical activity. And the second is the social environment. So in the sense that what income levels are you in? So there is a lot of epidemiological evidence that income does play a role in how active you are and what kind of a culture you belong to. And then there are some health equity factors that also affect your physical activity. And then the third layer is the built-in environment. So whether the physical context you are in, example, whether you have good neighborhoods where you can walk, or you have good access to parks and green spaces where you can walk, also affects in a particular way in certain senses how active you are. And then there is also the last layer of natural environment. So in this talk, I'm going to talk about two different determinants and then the interventions targeting these two determinants. One is the individual level determinants, and the second is the built-in environment, meaning that we'll also explore whether a particular physical context, does it play a role in increasing physical activity or not? So the first study that I want to introduce you is called the BSMART study. So this was, so in United States, there is the prevalence of cardiovascular disease is a big problem, a challenging problem. And then under the age of 60, it's approaching almost 40% of prevalence. And 1/3 of the CVT deaths occur between 55 and 64 years. So the idea of this study was to improve physical activity among this midlife adults to prevent an occurrence of CVT. So one of the approaches that we took in this study was the human health coaching. So the human health coaching, to give you a broad introduction, is mostly a client-centered approach. So what happens in human coaching is you actually sit with a coach and then you form personalized health goals of what you want to do, what are your strategies, and what are your barriers to physical activity. So it's more like an individualized, and it comes more from the client rather than the coach actually giving you these physical activity goals and plans. So here's an example of a physical activity goal you set in a health coaching session. So over the next 7 days, 3 times a week, I'll walk for at moderate intensity for 30 minutes. And then on Mondays, Wednesdays, and Fridays at 6 a.m. So there are two things in this particular sentence that are happening. One is you're fixing a goal in the sense that I'm going to walk 3 times this week and I'm going to do it at moderate intensity. So that's called a goal. And then the second part of the sentence is like saying that's called an action plan, meaning that when are you going to execute it and how are you going to execute it? So in this case, it's mostly on Mondays, Wednesdays, and Fridays, and that this particular time. And then you can also specify what kind of action you take in the sense that do you want to run, do you want to cycle, do you want to walk? So that forms an action plan. So the reason why health coaching is effective is because of the specificity that you give when you actually develop these goals. And then you also sit and talk with the health coach about a coping plan in the sense that what happens when one of the activities are missed. So how do I cope with the missed activities? When do I execute it? What are my barriers if I actually miss out on one of the goals? So even though it is effective, so there are some limitations of human health coaching. One, scalability in the sense that there are not enough coaches for the amount of population we have. And the second, the cost, which is, I think, is a major barrier in the sense that the cost benefit analysis has revealed that almost it takes around $60,000 per year to improve like a quality of life for chronic disease patients like stroke and heart diseases. So, and then there is also the problem of infrequent meetings, meaning that these healthcare sessions are usually like 40 to 45 minutes or 45 minutes to 1 hour, but these are done only once a month or maybe at most once in 2 weeks. And then there is also the traditional health coaching method. There is also a lack of objective data. So the patient comes in or the client comes in and reports that I've done a particular amount of physical activity, but there is no objective way to verify it. So one of the biggest, primary aims was to actually create a semi-automated coaching system to reduce, so from a cost-effective point of view, meaning that, so it is not a fully automated system, meaning that we still have some human coaching, but the idea was to get the initial human coaching session where the client sits and then forms the goal and the action plans, and then the rest of the coaching sessions are taken over by the automated coach. So here's an example of a concrete example of physical activity goal in our BSmart problem. So you complete one bout of 20 minutes. So when I use the word bout, it means that you're supposed to be in the target heart rate in that 20 continuous minutes that you're doing physical activity. So we customize the target heart rates based on personalized age. So we calculated that all of the goals were moderate or vigorous intensity. We did not take in the light physical activity into account while framing these goals. So as I said, so it's a semi-automated coach. There are two parts to it. So the human part comes in the beginning of the study, where the client sits and then, or the participant sits and sets the goal, and then the initial action and coping plan. And then the rest of the goal modifications and the dialogue functionalities are mostly automated through the BSmart coach. So there are three devices that we used. One is the Fitbit tracker to get the objective heart rate data. And then we used smartphones to communicate these messages. So the messages could look something like on the left that you're seeing. So this is the end of the week goal completion message saying that, hey, this was your goal for the week and then you have completed all of it. And then now do you want to improve your goal because you've already achieved it? So do you want to make it more challenging or do you want to keep it the same way? So there are also other messages throughout the week, like at the starting of the week, we remind that, hey, this is what you're supposed to do. And then in the middle of the week, we send some reinforcing motivational messages saying that, hey, you're on your way. This is what, you're doing good and stuff like that. So how do we build this? So this is talking about how do we build this kind of, automated health coaches. So for that, we adopted a multi-agent approach. So a multi-agent, you can assume that each participant has his own digital coach. So that's what an agent represents here. And then for each different agent, these agents can be heterogeneous, meaning that for your own preferences, your coach could suggest you something which is customized to your own preferences. So these agents can run both on the server, on the mobile phones, and on the watches. So the advantage of using this multi-agent architecture is that it's scalable, meaning that you can deploy thousands and thousands of agents on edge devices and some of it on the servers to really scale, and then it really acts as like a personalized health coach. So this is a glimpse into what really happens inside an agent, in the sense that when you're deploying it. So a part of this on the left side, if you see, so there is a planner and a scheduler, meaning that part of the coach, the automation part, will help you actually plan your goals, and then it will also give you messages at particular times, meaning that it schedules that, hey, on Monday mornings, this is what the message is going to go. And then on the midweek, this is what is going to happen. And then there is also the part of learner. So this was something that we were working on many different types of physical activity interventions. So we wanted to do something which more accommodates all of these interventions in a single architecture. So that is why we call this a template architecture. And then for different instances, what we did was we instantiated some parts of these architecture and then made different types of health coaches. So we, on the right side of the the architecture, you see the context analysis. So this is the part I was talking about, where some of the coach can run on the edge devices, where you do the context analysis part, meaning that you're wearing a watch or you're carrying a mobile, you can gather the GPS data and then intervene accordingly based on that particular context. So we tested this on different populations. So one of the CVD populations, we worked with healthy adults, and then we worked with disabilities. And we also worked with different wearables, Fitbits, Apple Watches, Withings devices. And all of these are module components. So you can plug and play, in the sense that you can remove certain components for a particular type of intervention versus there are certain components present in some types of interventions. So this, as I said, is an instantiation of the previous architecture, the template architecture you saw. If you see, there is no learning component to the BSmart architecture, but I'll show you a different intervention in which we have the learning components. So here, because it's mostly on action plans and coping plans, so the planning and the scheduling components are present. So this is the scheduler which actually times the dialogue. So the underlying, the tech is mostly finite state machines. We didn't go anything complicated. It wasn't necessary for this intervention. But you can assume that you can do something in NLP, or now with all the large language models, you can assume that you can run some, large language models on the agents. So this was the BSmart trial design. So there were two components to the trial. So there was a 4-week acceptability study. So this was mostly to determine the usability and the acceptability of the system, the BSmart system. And then we also took some feedback, and then we kind of iterated and then improved it for the next randomized control trial. This was a feasibility trial. We were hit by COVID, and this was right in the middle of the COVID, so we couldn't really recruit all the participants that we wanted to do the control versus the intervention group. But I'm going to show you some results of the acceptability phase, and then I'll show you how we built out a new intervention from that results. So this is the BSmart trial recruitment. These were the inclusion exclusion. So as I mentioned in the motivation, so we were looking for people who were prone to cardiovascular diseases. So either they should be on stage 1 hypertensive, or they should be pre-hypertensive. And then they're all middle-aged people, ages from 35 to 64. And then the last one was they should be physically inactive, meaning that 100 minutes of moderate to vigorous physical activity. So this target heart rates were basically calculated on the personalized target heart rates of each individual. So these were the results. So we did not see much of a difference in the moderate to vigorous physical activity from baseline to post-intervention week. We saw a significant decrease in blood pressure. So that was one of our secondary outcomes. And then I'm going to talk more about the percentage change of weekly goal achievement, and system ratings were pretty good. So here is the average goal achievement. When you look at, so when I say goal, remember back that your goal is something like, hey, I want to do 3 times of physical activity, maybe like 20-minute bouts, and three different bouts of 20 minutes each in moderate or vigorous physical activity throughout the week. So what this table here is showing you is that how many percentage of bouts did the participants successfully complete. So if you see, the percentage was around 42%. It's not the result that we expected, but it's still a decent result in the sense that we are taking someone who are not physically active, and then they did some physical activity. But our intention was to actually see why is it that these people only had 42% of the goal completion rate. So what we did was we did a post hoc analysis. So in this, we removed the notion of a bout. So what we did was we only looked at how many minutes of physical activity did you do in moderate and vigorous heart rate ranges. So to give you an example, so your initial goal was 23 times a week. So in the previous table, what you were seeing is how many of those bouts did you successfully complete. But in table 2, what we did was we relaxed that notion of a bout, and then of the 60 minutes in a week, how many minutes were you actually in that target heart rate zone of moderate or vigorous physical activity. So what we saw was there was an increase to around 81%. So that was a little bit weird. So what we did was we redefined the notion of a bout. So instead of a complete bout, what we did was we defined a new bout called a partial bout. For example, if you were supposed to do like 20 minutes of activity, so what we did was, let's see if they even did like 10 minutes of activity, and then if that contributed to this 80 or 82% of your physical activity minutes. What we found out was a lot of people were actually trying to do these bouts, but weren't fully successful in completing the bout. And then there are always the cases where the participants failed out, did not try to do that bout also. So pictorially, this is what it looks like. So this is what your initial action plan is. And then if you were trying to achieve this 20 minutes, but you kind of executed it in different smaller bouts. So this is in behavioral theory, this is mostly called a lapse. So a lapse is where you try to set out to do something, but you don't do it. And this is like an extension of a lapse where you're trying to do something, but you are not completely successful in doing that. So this graph here is showing you, so there is in the planning literature and in the computer science, there is a technical term to calculate how different your plans are, meaning that how different is your initial plan that you set versus what you have achieved. So here 6 on an average represents that your 6 actions different from the initial plan that you actually planned for. So that means that what this signifies is that when in the process of behavior change, there is a lot of dynamism in the sense that what you set out to achieve and then what you achieve varies very, very significantly. So our idea was, what if we actually help these people with the lapses? Meaning that while we notice that somebody did not achieve their intended action, why don't we actually intervene at that right moment, in the very moment, and say that, hey, I know that you did not achieve what you planned to achieve. Why don't I give you a recommendation saying that, why don't you achieve it at another time point with some self-efficacy messages saying that, hey, it's completely fine. This is very, very normal to lapse and behavior change. So the idea is going to look something like this. So the first on the topmost part, so this is your initial action plan, 20 minutes 3 times a week, and then Monday, Wednesday, and Friday. So here comes Monday, and then you only achieve like 10 minutes of your intended 20 minutes of activity. So what the intervention does is it's going to give you an alternate recommendations by restructuring the rest of the plan, meaning that you could either reschedule that rest of the 10 minutes to Monday night, or you can combine 10 and 20 minutes and then split it into 15 and 15 minutes into another recommendation. So this is the core of the idea that we have been working on, meaning that how do we develop these kind of interventions? So if you see, the flavor of the problem is very similar. So when we looked at the literature, we first wanted to see if there was, if people had actually tackled this kind of problem. So, and then we came across the Mars rover domain. So what you see here is the Mars rover domain. So it has a very, very similar problem that is an open problem in computer science literature, meaning that scientists from Earth send these action plans to the rover at the beginning of the day. And then because of the uncertainty in the execution and then the environment in the Mars, not all of the actions get executed successfully. So let's assume that you want to move the rover from point A to point B because of there is some turbulence in the terrain, or there are some other conditions in the terrain that it may not be able to reach point B. It might reach somewhere half a distance or something. So the problem is the same. What happens, I mean, like, how do you cope with these kind of, what happens when you partially or completely fail when you want to do a particular activity? How do you replan and then reschedule it? So that was that was mostly my thesis, how to come up with these planning and scheduling algorithms that adapt to these users. So the key to building such algorithms is preferences. If you go back to the example, it's mostly like, how do you decompose, in the sense that if you fail some action, you might want to do it on the same day versus another day. So this is mostly a preference of a particular individualized user rather than a hard written rule. So what we wanted to see was, so we went back and did a human health coaching sessions transcript analysis. So if you remember, so when I was talking about human health coaching, most of it comes from the user or the client, meaning that they sit down and tell that, hey, I want to do this on this particular day, and I prefer doing this rather than doing something else. So we identified, when we did the thematic analysis, we identified 3 different themes of preferences. So the first one was preferences over actions. Second one was preferences over goals. And then the third one was preferences over coordination. And I'm going to talk a little bit more about each. So here, a preferences over action, meaning that let's assume that you want to walk for 30 minutes, and this preference might depend on what context you are in, whether it's sunny outside, where you're at home, you might want to what you call walk then, versus when it's rainy and it's home. So these things actually differ from user to user, and not just walking. So you can have a preference over what kind of activity you do too. So that is the preferences over actions. And the second part is preferences over goals. So if you see, the same 30 minutes can be decomposed into multiple different ways, meaning that you can split it into 15 versus 15, and then you can do a bike of 30 minutes, you can do a run of 30 minutes. So what you're essentially saying here is what the participants expressed is we have a preference over how we decompose these goals, and then what kind of actions we take. And the third one is preferences over coordinations, meaning that some people might prefer walking with someone else rather than walking alone. So what this is saying is that you have a preference of the same activity, more doing it with another person than doing it alone. So now that we had this preferences which we identified, so the next thing is the question arises, because these are open problems, so how do we actually solve this problem, the dynamic coping problem? So the one obvious solution would be people who are familiar with the Markov decision process. So you can code the preferences as reward values, meaning that, hey, I'm in a particular state, that I am at home, and then I want to walk. And then for that particular context or particular state, you can assign a preference value, and then you can compute an optimal policy and then give you an intervention. The problem with MDPs is that even though they give you an optimal solution or an optimal policy, the problem is that they take a lot of time to actually compute it. And as I said, so one of the problems with this, both the Mars rover and the physical activity domain, are the edge devices do not have they have limited computation. So you cannot run hours together of a policy to actually learn and converge. So the second approach you can take is a continual planning, meaning that when something fails, you can go back from the scratch and then start replanning it from the scratch again, which again is very computationally intensive. So the third alternative, and the alternative that we chose, was essentially doing scheduling with alternatives. So meaning that when you plan with alternatives and then send it to the scheduling. So something goes wrong, you have like a bunch of alternatives that you can quickly, what you call, repivot to. So here is in the classical planning literature. So here is, if the environments are very deterministic, this is what is going to happen. So you have a goal, you have a set of actions, you have a planner. The planner gives you, okay, what actions to take, and the scheduler will tell you when to do those actions, and then the executor is going to execute it. But that's a static environment. In dynamic environments, because there are a lot of failures, so you'll have to go back to planning again and again and again. So that's where scheduling with alternatives, meaning parts of action plans, and then reacting to the moment, is more beneficial and less computationally expensive. So these are, as I mentioned, these are one of the advantages of using scheduling with alternatives. So you have opportunistic optimizations and proactive adaptation. So you can, all I've been talking about is reacting to something going wrong. When you have scheduling with alternatives, you can also proactively adapt, meaning that, for example, so you have a planned activity on Wednesday morning at 6 a.m., but the weather says that, hey, it's going to rain. So instead of waiting for you to not do the activity, the health coach can automatically, proactively replan it, saying that, hey, I know that it's going to rain and then you won't be able to walk outside. Why don't you, do it on Thursday instead? So instead of you actually failing the action and then reacting. So that's a proactive adaptation of the plans. So now that we have identified these preferences, so the next thing that we wanted to do was, how do we actually, so I showed you pictorially and then explained you what these preferences are, but the algorithms, when you have to write algorithms, they do not understand these. So what you need to do is you need to come up with extensions to planning languages. So one of the planning languages is called task analysis, environment modeling, and simulation. So this was mostly developed in 2005 to 2010. So this was a DARPA coordinators project. So this was originally developed for the fast response teams and unmanned missions. So it's mostly a very coordination oriented project. And then it serves as a language, and then it also gives you this simulator toolkit where you can actually simulate these different scenarios of multiple what do you call action plans, and then multiple goals, multiple different varied action plans, and what happens, how do you write, what do you algorithms to maximize these preferences and stuff like that. So here's a full task structure of a CTEMS. Now I'm going more abstractly because now it is more domain independent, and then you're talking really about a planning language rather than a specific intervention. So here you have different subtasks, and then the things that you see on the labels: disables, enables, facilitates, and hinders. These are called coordination effects. So meaning that a method or a subtask can disable another method. If you do something, you cannot do another part. Or if you do something, then that will enable you to do another method. Facilitates and hinders are called soft relationships, where you do some activity that might really help you to do another activity. For example, in the physical activity context, so if you warm up, you might be able to run more or something like that. And then hinders is where you actually do one thing and then it actually hinders your quality or the other method. So we set out, because the CTEMs did not have preferences, as I was mentioning, this is an open problem. So we set out and then we wrote these language extensions for each of these categories: the preferences over methods, accumulation functions, and preference over the non-local functions. So here's an example, and then these are all the mathematical extensions we wrote. So these, for example, the method 1, you can probably say that this is how you represent as a tuple, in the sense that this is the preference value and this is the context. This is the preference value and this is the context. So that's how you mathematically represent it. And these are the accumulation functions. So P max here, for example, is going to say that, hey, of all the subtasks, like I showed you earlier, you can decompose a particular sub-goal into different sub-goals, and P max will help you choose which most decomposition of a particular over all of the subtasks and methods. So here's an example as I was talking about. So on the left side, you see that the 8,000 steps for this particular user has the most, this is the most preferred decomposition. So it's split into 4,000 and 4,000, rather than 8,000, and then there is the 8,000, which is P-sum. P-sum is 8, 2, and 10. So when you're writing these algorithms, so when the algorithm searches for the maximum, what you call preferred decomposition, to give you those alternate plans when something goes wrong. So here is the mathematical extensions of these non-local effects. So I'm just going to talk about synchronicity. So synchronicity is saying that, hey, when you walk with someone else, then it means that your preference value is going to be increased. So this is one way to represent it. And then there are some coefficients, and then there is this time because you're doing it later. So, and then after, so at the end of this part was till the end of the slide was mostly extending the language itself. We haven't yet written out the algorithms. So we came out with different sets of algorithms to actually use this language and then give these most preferred alternatives when something goes wrong. So here is the problem structure. So meaning that the first one, so there are 3 conditions. So the accumulation of qualities of the picked methods will sum to goal, meaning that, so in all of these task structure in the problem, so you have a continuous goal. So the continuous goal in physical activity domain is mostly how many minutes that you want to work out in this particular week. Or if you take the Mars rover domain, it's the total amount of energy that the rover has. So each activity when you do, there is a certain amount of energy that gets consumed. So, and then there are temporal constraints that should be satisfied, meaning that you cannot schedule like 2 workout sessions back to back. So for a lot of people, I mean, like you need to wait out a certain amount of time before scheduling one. So that's a hard temporal constraint that needs to be satisfied. And also the most important objective is when you're picking out these alternate methods, you need to pick out such that you pick out the most preferred alternative method rather than just picking out some arbitrary method. And then the dynamic coping problem also has the same above criteria, but the only difference is that you are given with an optimal schedule or the plan, and then something goes wrong, and then you pick another alternative from whatever alternatives that the algorithm is. So here is a full pipeline that we have built to what do you call to execute these algorithms. So it gets converted. I'm not going to go into too much technical detail here, but if you're interested, please shoot me an email or you can ask me in Q&A. I can go into more. I can dive into more details here. So essentially, what happens is you're scheduling here. So you're converting into graph problems, and then you're doing some consistency checks, and then you're spitting out some preferred schedules or plans. So to do this, all of these experiments were not on humans. So these were all simulated tasks. As I mentioned, CTEMS also gives you this. So you can generate these random task structures to simulate these different situations. And then we can see how the algorithm that you've written behaves, in the sense that whether it gives you optimal solution or a near optimal solution. So the things that we compared with were gaps with alternatives. This is one of the existing state-of-the-art algorithms. And then we extended with alternatives. The gaps did not originally have some alternatives. And then CTDS and CTDELS is the heuristics that we introduced. And then there is the random part. So the way we varied the parameters is constraint density. So when I say constraints, so I was talking about the temporal constraints. So the temporal constraints, so for some people, your schedules could be really, really tight, and then you only have like very little time slots that you can work out with. So constraining, so changing the density of the constraints and how many this thing can actually accommodate in those particular scenarios. A number of alternatives is when something goes wrong, how many alternatives do you have? I mean, like once you miss out an activity on Monday, you can only schedule it on Wednesday again. So that could be one of the like alternatives for a particular person. Whereas for another person, you can have more alternatives where you can do Monday night, Tuesday morning, Tuesday night, something like that. And then the preference levels. So as I skipped some of the technical details, the preference levels is mostly how preferred is a particular method or a particular task is relates to that preference level. So here are some of the results. So if you see the CTDS and LH, so what these two do are heuristics. So when you do the gaps with the alternatives, it takes hours together to run. So what we wanted to do was we wanted to get something near optimal, but we wanted to do it in milliseconds because we wanted to run these on wearables and other limited computational devices. So what this is saying is, so the CTDS approximates about 80% of the optimal preference value, but it does it in like really, really less amount of time. So again, we varied the number of alternatives, and then we tried to see how is the preference values of the overall restructured plans. And this part is when we varied the preference value, meaning that when we change the different preferences, different levels for different activities, how would the algorithms perform? In all of these cases, CTDS performs almost 80% to the optimal solution, but it does really, really quickly. So as I mentioned, these are all computer simulations. So what we are currently working on is actually running these on human survival. I mean, like actually humans. So we took a stroke population, and then I'm working with, he's my mentor, Dr. Zand. So we initially sought out to test this on stroke population, and when we looked at the literature, so we found out that there is not much supporting physical activity literature for stroke survivors. So we went ahead and then published a few articles on to see whether, okay, how much of physical activity do stroke survivors really do? So we found out that in our analysis, almost 30% of independently mobile stroke survivors do not actually meet physical activity recommendations. So these recommendations were given by AHA, American Heart Association, and American Stroke Association. And in one of our analysis, we did all of these analysis on BRFSS dataset, so which is the nationally available public dataset, and this was over the years. So there were a few interesting results that we got, in the sense that there are only certain physical activity recommendations that varied by the age groups, meaning that older people were more prone to doing some set of recommendations versus younger people were more prone to doing some set of recommendations. And then we also saw, I mean, like we also wanted to analyze how physical activity improves mental health. So all of these kind of are epidemiological evidence that it is important to do physical activity interventions for stroke survivors. So here is the second part of my talk. So as of till now, what I've told you is like how to build these physical activity interventions targeting the individual determinants. So the mostly comes under your psychological, improving your self-efficacy. Okay, how do you? So the next set of interventions is mostly built on, targeted on the built environments, meaning that the specific question that we wanted to ask was, does physical context play a role in enhancing physical activity? Physical context, when I mean whether you're at work, whether you're at home, whether you're at a park, whether you're at a gym. So if I intervene in these specific physical contexts, so would it help to increase physical activity is the question. So to give you a brief, I shouldn't like, so this is an introduction of just-in-time adaptive intervention. This is a paradigm of interventions that is currently like very, very new to the field of physical activity. I don't, to my knowledge, there are no randomized controlled trials which actually test the efficacy of this particular paradigm of intervention. So you can assume that these are really new. So the idea behind just-in-time adaptive interventions is, so the intervention should be delivered in the real time, and then it should accommodate users' preferences over different contexts, and then it should be triggered autonomously. So if you go back to the coping intervention, that also what you call comes under this just-in-time adaptive interventions paradigm, where you're actually intervening in real time, you're looking at user preferences, and you're doing it autonomously rather than somebody doing it from behind the scenes. So this was one of the pilot studies that we did. All of these are kind of pilot studies. So this was back when I was doing my thesis. So what we wanted to see was whether as I mentioned, whether a particular physical context does it play a role in reducing sedentary behavior. So in this case, we did not look at physical activity. So the experimental setup, I do not have that much time to go over the entire experimental setup, but I'll just tell you. So in the sense that we wrote out a smartphone application, and then every time a user was sedentary, and then the users were tagging different locations where they were, in the sense that whether they were at work, whether they were at home. We started intervening and then asking them to what do you call stand up. So this is reducing sedentary behavior. So it was just standing up. So and then we did an analysis, and then we saw there is a significant correlation between the context or the physical context of the user and actually reducing sedentary behavior. So this was our kind of preliminary evidence to develop our next intervention. So the next intervention, what we thought was, okay, so there is this physical context that plays or correlated with sedentary behavior and physical activity. So the base idea of the intervention was, hey, why don't I actually exploit the current physical context you are in, and then give you an intervention to improve your physical activity. So the intervention looked something like this. So what we do is, because with the variables, you can detect whether someone is walking. So what we did was, hey, we catch the people right in the moment of they are walking, and then we say that, hey, it looks like you're already walking. Why don't you walk a little bit longer? So this is the base idea, meaning that this is not structured like the other BSmart intervention where you're doing action planning, scoping plannings, you're sitting down and saying that. This is more like a freestyle kind of intervention where you're exploiting and then trying to see if somebody can improve physical activity while they're doing that activity. So this is the agent level architecture. So if you remember the template architecture back, so this has no planning and scheduling modules, but this has the context analyzer and learner modules, so which is used to learn. So I'll tell you in more detail about what is the learning that is happening. So we divided the study into three different phases. The first phase is the observational phase. So in the observational phase, there are no interventions provided. So for instance, if you're walking every day from 5 to 5:20 p.m. walking your dog around your neighborhood. So what the observational period is going to do is just observe that, okay, this is the amount of distance that you walked for this particular time in this particular context and on every single day. And then the next comes the training phase, which we call the JIT phase. So there is a difference between JIT, just-in-time just-in-time interventions, and just-in-time adaptive interventions. I'll tell you what the difference. So in the just-in-time interventions, what we did was we tried to exploit that behavior where you're walking. So whenever you were walking in any different context, we tried to tell that, hey, why don't you walk a little longer? I know the weather is good, the calendar, you do not have any events in your calendar. Why don't you walk a little longer? So that kind of made our training data. So that we compared this, what do you call, interventions, and then we saw whether there was, because we had a baseline, we compared it with the baseline and saw, and then determined whether the intervention was successful or not. So what we did was we kind of used these data points to actually train for the next phase of the study, which is the tailored JITI, just in time. This is where the adaptive intervention part comes in. So meaning that you're learning which context to exploit to give the intervention rather than giving it all contexts. So this is still going on. We did it on healthy adults, and these are the results for some of the participants. As the study is still going on, I cannot give you the full set of analysis, but the idea was to communicate what is the idea behind this intervention. And then we see some improvement in the sense of JIT phases and the just-in-time adaptive phases. So here are some my other research projects. So I also work on EHR data. So one of the projects that I'm working on is machine learning prediction of recurrent strokes using the EHR data. And then I'm also working with, so the PIs in these projects are Vida, Betty, and Raman Zand. And then I'm working with Kristen on a Pennsylvania maternal and infant health in a pandemic project where we're trying to define a digital phenotype to assess whether somebody is pregnant or not. And then we also have a few other projects. So we are always open to collaboration. So if you want to work on any of these projects, or if you're interested in wearables, please shoot me an email. Thank you.
Thank you. So now let's open up for the questions from the audience. If you have questions, you can just unmute yourself and also turn on your camera. All right, so it's a very like a great overview of the wearable technology capability to improve physical health or physical activity. So, Ajit, so I'm wondering, when you design this health coaching system, does it take a lot of time to develop when you collaborate with the clinical investigator? How much effort?
So when we're developing, especially the server and the technological part, we don't need that much of an input from the clinical side of this thing. But when we actually start running it on the human subjects, that's when we need a lot of input from the clinicians and also the participants themselves. So we are also planning to do some qualitative studies on how to design these interventions like how should the interface be, and then what kind of messages should we send so that motivates these people. So in those kind of aspects, we really need the clinicians' help.
So you also talk about how can you say you can scale it up to be used in a larger cohort population.
Correct.
So does it mean that you can do this deliver this onto maybe a study with like 1,000 subjects? Is that?
Yes, easily. I think you should be able to do it on tens and thousands of subjects at a time without any scalability issues. You're essentially decentralizing the computation across devices, so it's very easy to scale.
I see. That's wonderful. So you mentioned about the semi-automatic, automatic. The semi part is like it's not just you can run something automatically to identify what's the optimal strategy. So there's like some other like a human expert input. Is that
Correct.
right?
That is correct. So that's why we are not at a stage of fully automating it. We still need to, like I was talking a lot about preferences, and then what if something goes wrong and then you choose the next preferred activity. So the preferences are still elicited from the user. We go set and ask initial set of preferences. That okay, if you miss this, how is it that I mean, like, what is your next best context? But over time, you can learn that, in the sense that in the second part of the talk, I was talking about actually comparing with the baseline and then learning which context is more favorable to you. But in the initial phases, you need to, what do you call, elicit from the users, and then a health coach should sit down and then come up with the initial action plan and then coping plan.
All right. Harry, go ahead.
Hi, Ajit. Very nice talk. Thank you. So yeah, one question with two parts. First part, the preferences are solicited from the users, and the preferences consist of basically some of the example you gave was, say, 2 or 3 times a week, 30 minutes of moderate walking such that heartbeat is raised. That's the example of the preferences, right?
That's the example of an action plan. And then preferences is also, yes, part of it is also preferences, meaning that you chose to do it on a particular day at a particular time.
Okay. And you're saying that part of the updating in the algorithm is you observe what the users actually do as opposed to what they stated as their initial preference. And that allows the algorithm adapts for that.
Correct. That is correct. Yes.
Okay. And when you do, a trial like with Dr. Zand, what is considered your reference or control group that you're comparing, your approach with?
So our reference group would be something which is standard care. So in stroke without any, or you can have a reference group where there is just the human health coaching part without the active adaptation of the coping plans. So, but when we wrote this particular piece of research grant, so our reference group was the standard care.
Okay, and what is the final metric by which you determine success or not when you're comparing your treatment group to the control group?
Correct. So, so we are still in the stage of feasibility. We are not in the stage of efficacy yet. So in the feasibility stage, so it's the response rate for now. So that's our primary outcome. So when we give an intervention, how likely or what is the percentage of the people that are actively responding to these messages, interacting with the wearables, and then, so that is our primary outcome. But I mean, like, if you zoom out and then if you're designing an efficacy trial for this, it would be how many, I mean, like, weekly goals did you achieve? How many bouts did you actually actively do? So your efficacy part is mostly related to your goal progress, goal achievement.
Okay, so for now, feasibility is engagement and use of the algorithm.
Right.
But later on, when you do test efficacy, you'll be your outcome will be kind of rate of achievement of stated goals.
Correct.
Okay, thank you. Well, with the advent of wearable technology, which is here to stay with us, it sounds like there are a tremendous number of applications and possibilities for where your algorithm may be useful. Are you finding that as you communicate your findings to the community?
Yes, I think we have gathered a lot of interest from different, not just physical activity, but I think this can be applied because lapse is a very common thing across behaviors. And especially the coping part, we have gathered a lot of interest from different sets of groups.
Very exciting. Thank you for sharing this with us.
Thank you so much.
Yeah, thank you for taking time presenting this very timely topic to us. Thank you, everybody, for joining us today. If you have any questions or would like to collaborate with our speaker, please feel free to reach out to him by email. Our next BERD seminar will be on September 22nd, which is 2 weeks from now. We look forward to seeing you all then. Thank you.
Thank you so much.
Thanks. Bye-bye.